Okay, hello everyone and welcome back to Advent with Code, Yeah, today day 8 with Golang. So let's start diving into our problem of today. So the expedition comes across a peculiar patch of tall trees, all planted carefully in a grid. The elves explain that the previous expedition planted these trees as a reforestation effort. Now they're curious if this would be a good location for a treehouse. Okay, treehouse sounds fun. First determine whether there is enough tree cover here to keep a treehouse hidden. To do this, you need to count the number of trees that are visible from outside the grid when looking directly along a row or column. The elves have already launched a quadcopter to generate a map with the height of each tree, your puzzle input. Each tree is represented as a single digit whose value is its height, where 0 is the shortest and 9 is the tallest. Okay, so basically this is like a map probably. A tree is visible if all the other trees between it and an edge of the grid are shorter than it. Between it and an edge of the grid. Okay, so edge is basically here the right side or top. Okay. Only consider trees in the same row or column. That is, only look up, down, left or right from any given tree. So we don't have any diagonal line of sight that we need to consider. Okay. All of the trees around the edge of the grid are visible, since they are already on the edge. There are no trees to block the view. In this example, that only leaves the interior 9 trees to consider. So, okay. Makes sense. So the top left 5 is visible from the left and the top. Yeah, because there's a 0, there's a 2, and this is the 5. Makes sense. It isn't visible from the right or bottom since other trees. Yeah, okay, this is 5 and this is 5, therefore it's not visible from that. The top middle 5 is visible from the top and from the right. The top right is not visible from any direction because it's smaller than the 7, smaller than the 5, smaller than the 2, smaller than the 3. Or the 9 here. Okay. There would only be trees of height 0 between it and an edge. The left middle 5 is visible, but only from the right. Yes. The center 3 is not visible from any direction. Yeah, makes sense. And the right middle 3 is visible from the right. And then in the bottom row, the middle 5 is visible. And, let's go back. With the 16 trees visible on the edge and another 5 visible in the interior, a total of 21 trees are visible in this arrangement. Consider your map. How many trees are visible from the outside grid? Okay, so it's basically taking this grid and then find out how many trees are visible. Okay, this sounds about doable. So let's start. First create our new input or test.txt file, which contains our test data. So then start our application. day08.go. Okay, and maybe we should also directly fetch our input to see how big the input data will be. your puzzle input. Oh, this is not that small, actually. Okay. Copy and then close it. So let's start. So how would we do this? So basically, so if we think about how would we implement this, then basically we need to, if we reach a tree that is 9, right, then we already know that from this side no tree is visible. So visible can be only trees. So yeah, let's start thinking about that. So we have to check this for every row from the left side, from the right side. And we have to check it from for every column, from top and from bottom. So this is basically how many checks we have to run. So, and then what we would do is basically count the numbers of trees that are visible in this line. So if we go from the left, for example, then we would start with 2, and we know, okay, this is the outer edge, so therefore it's always visible. So then we go to 3, where we see, okay, this is higher than what we had before, so therefore this tree will be visible again. Then there's a 3 and another 3, so basically they are not visible. Then we go to 1, which is not visible. Then there will be 4, where we know, okay, this is also visible because those trees are all trees that came before are of smaller height. So therefore we go through each line and always keep track of what was the highest tree that we encountered. And then basically count the individual trees that we find along the way that are visible. And we do this from left side, from the right side for every line. And the same we do this from top to bottom. And okay. Sounds not too complicated. Let's see how we can implement that. So if we look again at our input data, then we see, okay, we need to read those things line-wise again. So we start with our standard template that we use as well. Input file error, and then basically os.open. We start with our test.txt until we find the correct result. So if error not equal nil, then just panic. And then as we need to read this line-wise, use our scanner. So scanner, and as always, defer input file dot close. We have our buff.io new scanner with the input file. And then for scanner.scan line equals scanner.text. Sorry, I'm a little bit not 100% fit, but okay, this will get better, hopefully. Okay, we have our line. So now we pass each individual line, and then we get a part of the grid. So what we have our type that we call, just call it grid struct, which has the individual lines or the individual fields, probably fields and fields. I don't know exactly how this works, but I think this should work. So if we say, okay, our fields is basically a two-dimensional slice, so where we have something in x direction and in y direction. So we create our grid up front, grid, and then we basically add a line or pass a line and then create a grid out of it. So for that we create a new method, pass grid line, where we hand over the line and our grid. So since we want to modify the grid, we use a pointer here. Create function pass grid line. Maybe we do this on top. Okay. So now let's convert all those individual lines into a string. So we first create our string into the individual numbers. So first we basically create our row. Let's say this is int, and this is of size. We know that basically we need to use the length of our string, of our line, right? Because basically this length is the length of the number of heights that we need to store, so we can just reuse this. Here again, move this over maybe a little bit smaller so that it doesn't hide anything that we need. Okay, so we have our row, and then basically we go over the individual lines, values that are in the line. So for field in line. Do we also need, I think we probably need again our range, and then field is index dot field. So, and then basically we just assign in our row for the particular index the value of the height that we pass from the file. So our file should basically field, or individual field is an int, I think. Unused variable int 32. So, but we need to convert it. So basically that it's 1, 2, 3 based on the ASCII table. This is something that we did already in the past, right? Do we know where? Where we converted between I don't find it currently. Okay. Okay, let's say field, and then basically we need to subtract the number from the ASCII table. So going back to the browser, we can check the ASCII table. Because the number that we get when we loop over the string will be the ASCII value of the character. So we have numbers from 1 to 9. So basically 1 will be 49. So if we get a 49, we need to get 1. So therefore we need to subtract 48. So if we take the value that we read and subtract 48, we should end up with the number that we are interested in. So let's see, field dot minus 48. Yeah, okay, this is int 32, so we use it in the same way, just use 32 bits. There should be, it's way enough. Okay, now we should have all the individual values within our stream, within our row, so we can add this row to the grid. So g.fields, and then we append here is equal append g.fields, and we append our row. Okay, so this is straightforward. So now we should in the end try to print out and see if our grid is actually what we would expect. So therefore format printf grid and then basically and then we have our grid. So, but for that we should also, we need to implement the function on our type grid. Func g start grid, and then let's call it just string, returns a string. And what we do here is basically just loop over those values, print those. So for row in range from g.fields, and then for field in range row, and then basically we just print and we print just our field value, which is an int, so maybe we just convert it to string. Does this work in this way? And then afterwards, when we have printed all the fields of one particular row, we just print out a new line. Oh, we can just do this. Oh, that's okay. Oh no, we don't want to print it. We need to add this, right? We need to add this to a string. So, okay, we do it differently. Result. I don't know how efficient this is because we are creating a string basically here. Usually these things are done in a different way where you have a separate buffer, because I don't know how this is implemented in Go. So if someone of you knows what would be a more efficient way to construct strings instead of just copying them over and appending always one field at the end, just tell me. Okay, so this is what we have. Now try to run it. First build. Okay. This doesn't look like what I was expecting. Maybe I need to do this that way. Okay, this looks funny, so not necessarily what we wanted. String conf I to A field. And this is something that we can convert. Okay, now it looks much better. Just casting to string seems not to work, so we can remove that. We don't need the cast. Okay, so let's compare it. Looks like it is actually the same grid that we have within our file. Okay, so this should also already give us some confidence that basically we can we can be sure that we are not reading something and end up with a different grid than we actually get as in our puzzle. Okay, now coming to the more interesting parts, basically trying to figure out how many different visible trees there are. So this is something that we can basically implement as part of a function for the grid. So we have our grid here and calculate or find visible, no, count visible trees, and this should just return a number. We only have trees in whole. So, and for that, basically, we have to do this in multiple steps. So, first step, count visible trees in rows from left to right. Then, second step will be count visible trees in rows from right to left. And then basically 3 count visible trees in columns from top to bottom. And fourth step is basically count the visible trees in columns from bottom to top. Okay. So let's try to start with the first step, right? So how do we do this? So we can basically use the same method that we actually do here. So we loop over the individual rows that we have. Then we loop over the fields. And then we also store what was the last, or let's say, what is the height of the maximum tree that we encountered when we were going through the line. So max height would be, we initialize this with 0, right? Because in the beginning we don't have any tree that is higher than 0. And then we also need to count. So how many are in the individual, or how many trees do we actually find? So I think it's just about the numbers, if I remember correctly. Okay, so, and how do we do that? Basically, this max height is something that we need to check per row. So we move this inside so that it is always initialized for each individual new row to be 0. Then we go over and we basically check if field is bigger than max height, then we know we found a new higher tree further down that basically is visible from the outside, from the direction that we are looking at. So therefore we need to increase our count So count plus plus. And we also need to store the height of this tree at the next, at the maximum height that we encountered within this run. Height. Let's move this if height. Okay. And 32. Okay, sounds not too bad. So basically what this means, we go from left to right. So this is basically because we read also from left to right, right? So, okay, so far so easy. In the end, we should have basically then the count of the trees that we can see from the left. So now we do the same thing, but we do it from the right. So in order for that, we need to change how we iterate over the rows. So we need to change that we basically don't look from the left, but we need to reverse the order within this slice. So therefore, let's take a look at Google, what it says about reversing a slice. Okay, there's no built-in function. This is a pity. Use a for loop to reverse a slice. Ah, yeah, okay, we can just... Yeah, okay, maybe we do this. We just basically go explicit with the for loop. This is probably easier. Now let's do it that way. Okay, going back, we no longer do this, but we... for x equals... and we start with len from row -1. So this should be the last element within our row. Then we say x minus minus, so that we decrease x for every iteration. And then basically we do this until x is larger equal than 0. So, and then we can say our height is equal to row from x. Okay, there's something wrong here. What is the problem? Unresolved reference x. Sorry. So let's look again. So it's... This is correct. So we define it. Oh, then... Ah, okay. I reversed basically the condition with the action. Okay. This looks much better. Okay, but basically it stays the same, right? So we have our loop, we have our max height, and we just iterate in a different direction throughout the row. So this should also give us the number of visible trees that we can see from the right. Okay, so far so good. So now it becomes a little bit more tricky, because we now need to do this not per row, but per column. So and for that, we can, we need to, we no longer have this, we no longer can just iterate about the fields, because fields is basically a slice of slices, right? Where the inner slices are the rows and the outer slices are basically the, the inner slices are the individual rows, right? So if we iterate over this slice, we only get it by row. So in order to make this per column, we need to loop explicitly over it. So, and this is something where we can use the same mechanism that we now used for going left to right. So where we say we start with the first column, then we do this until the number of columns is or the column number is smaller than the number of that the current column is smaller than the number of rows that we have. So which is g.fields, and we just increment the number of columns, and then we say our height is then not the row, but it's basically g.fields y and x. So, and here we also need to know how big the individual lines are, and this is then basically g fields from y. Okay, but now what we are doing here is basically, again, we are going from right to left. So we just copy this and use this here because okay, now I'm puzzled. Count visible trees in rows from right to left. Ah, okay. We loop over the individual columns. Ah, no. What I'm doing something wrong. Sorry for that. So, what we also need to do is basically change what is out and what is inside. So, okay, let me explain afterwards. So, basically on the outside, since we are looping over the columns, we need to go over the individual columns, right? And the columns are x here this way. So therefore, we always start with the first. This is from top to bottom. No, let's mean. We say, okay, we begin when x is dot fields is smaller. Oh no. We loop over the individual. On the outer loop, we just loop over the columns. So, yeah, so we go from the left to the right, and to the right, and so on, and so forth. Then, within the inner column, we start on the individual rows. So we start to look from the top. So increase our y coordinate further and further until we find something and count then how many trees we are seeing. So this is basically what we are doing here. Yeah. And then we also have to do this from the bottom side. So now we copy it, and then we just need to switch here that we go here in the different direction where we say g dot fields with the length, and we do -1. We initialize with -1, and then we do this until as long as y is greater equal than 0, and we do decrease this because this means basically going upwards, right? So we start first with our last row and then we go upwards. And on the way upward, we basically count how many trees we will find. Okay, so, and then in the end, we just return count. So now let's print out and see what comes out of it. Visible trees. Dot count visible trees. Let's see. Okay, let's run it and see what happens. 37. I'm not sure this is correct. Let's compare it to basically what was given within our "21 trees are visible." Okay, so this means we are somehow counting trees multiple times that we shouldn't count. Ah, okay. I see. We only need to count what is inside here, right? So because we know those are all, those on the outer side are always visible. So therefore, what we are currently doing, we're counting them multiple times. So if we count in this direction, then we count basically this tree and this tree. Here the 6 and the 3. If we count from the left to the right, we count this one, we count this one, we count this one, we count this one. So this means basically we are currently counting way too many. So how can we do that? So one way would be to basically make sure we are only considering what happens here inside. So we only count some tree as being visible if we are within this interior part. Okay, let's try this. For this, basically, we need to make sure that we don't count Okay, we can just make sure that we don't count all the trees from the first row. So let's give us our row number. So, and if row number equals 0, so this is basically the first row, or row number equals len from g.fields -1. So this means we are at the beginning or on the last row. So first row or last row. And these are things that we don't need to consider in this case. And therefore we should just basically ignore them and say just continue. So the same check is something that we need to do from the right. Row number. And we also need to do the same thing, but not with the rows, but with the columns. Column number, which is x, basically, x. max. So we ignore the first column and the second column if we are going from top to bottom and from bottom to top, so column wise. So when we now run this, then we will have probably less than 37, and I expect that we also are missing a couple of others. So my prediction would be that we have only 17 trees or something like that, because we are probably missing out some. Now it's 22 trees. Why 22? Okay. It doesn't help, just go through it. I think we need to debug and see what we are doing wrong. Okay, let's begin. We are here. So we start with our first row. And we know our row number is 0, so therefore we ignore it. So in the end we should go to the next row. And our row that we are currently looking at is the second one here, 2, 5, 5, 1, 2. Okay, we calculate the height of the outside as 2. It's higher than our so we have count is 1. Now we are at the next thing where we are at the 5. The 5 is higher than the 2 that we had before, so therefore this tree is visible as well. So therefore count plus plus, we have 2 trees visible. Okay, and now we go to the end of the row and nothing more is visible. So in this row only those 2 are visible from this side. So far so good. I would expect that to be true. Okay, next one. 6, 5, 3, 3. Okay, we should also return here only 1. So count, so we see our 6. Max height is 6, here max height is 5, so therefore this tree shouldn't be visible. Let's check if this is actually correct. The top 5 is visible from the left and from the top. Ah, I think we are counting trees multiple times here. Yes, okay, this is... Yeah. So the problem is that basically we count from how many trees are visible from the left, but we don't consider if those are distinct trees, right? Because this 5, for example, is visible from the top and from the left, but we should also only count it once. Okay. This means we should also that our check is okay, but how we sum up is basically not okay. Okay, we need to come up with a different way then. Okay, let's forget that. So this means just counting them doesn't work, because basically we have trees that are visible from multiple directions, and therefore we are only allowed to count them once, and we are currently counting them multiple times. Okay, this means get rid of counting. And instead, what we could do is basically just mark them so that we have our grid, and within the grid we mark them as if they are visible or not. And then in the end count how many of them are basically marked as visible. So let's change that. Let's say we have here now our grid is no longer just a int value, but we just create something like a tree which has a height, and we have some visible field is visible, And this is basically just a tree. Yeah. Our grid is a multi-dimensional tree, grid of trees. So then we need to do it in a different way. So basically now this is no longer the height, but it's basically our tree. And then we say the tree.height is greater than the max height that we already have. And then we don't change basically we need to make this also a pointer. So we then what we are doing, we are just marking this tree then as visible. And set this to the new tree height. So this means we can, without any problems, run the same algorithm or look at the same tree from different directions, right? Because this means we just set this to true. This flag is then equals to true, and we can set this multiple times. And then afterwards we go through the whole grid and find all trees that are visible, that have this flag being set to true. So this should make it easier. Let's see. This is basic. Oh. This is a tree. This is also a tree. And this is a tree. Yeah. Okay. So we need to get rid of those statements because they are not important anymore. And now comes the part where we basically just count in the end every tree that is visible or has this flag visible being set. Count. Row for tree, we don't have this anymore. And then we just check if tree is visible. Then we just do count plus plus. Okay, yeah, there are some problems when we create the grid, right? Because at the moment we need to create a tree here. Tree height and we store the address of the tree. Cannot use as type int, y type int, tree. And it's not tree, it's the address of tree. Need a trading comma, yes, okay. Try again. Compilation convert field to int. Where is this going? Okay. Yeah, when we print it out, this is also then a tree. And we just print tree dot height. As type int. We need to convert it. Okay, now it says we have 19 visible trees. This doesn't seem right. So, how many should have been? With 16 trees visible on the edge and another 5 in the interior, a total of 21 trees are visible in this arrangement. Okay, so it's not what we have. Okay. Let's create a different method to print out which trees are visible and which are not. Well, which we call print visible trees. So, and within there we just add if tree is visible, then we print out an X, and if it's not visible, we print out O. And then compare that basically compare this to grid.print visible field trees to what we okay, this doesn't seem right because everything in the outside should be visible. I don't know exactly why this and these are not visible. Let's check, right? Because this is 0, this is 0. Okay. We initialize with 0 and therefore something which is of height 0 is not correct. So we need to initialize this with -1 then, so that basically tree of height 0 is bigger than our initial height that we use. Okay. And now we are at the 21. So as we say, with 16 trees visible, a total of 21 trees are visible in this arrangement. Okay, sounds good. So then let's try to check if what happens when we run this on our puzzle input that we got. Visible trees 1560. Okay, looking into it, there are a couple of trees that are visible even in the beginning. No, in the middle there's a lot of space where there are not that many visible trees. Okay, let's see. We will see if this is correct. Submit. Yes, sounds good. Go to the part 2. Content with the amount of tree cover available. The elves just need to know the best spot to build their treehouse. They would like to be able to see a lot of trees. To measure the viewing distance from a given tree, look up, down, left and right from that tree. Stop if you reach an edge or at the first tree that is the same height or taller than the tree under consideration. If a tree is right on the edge, or at least one of its viewing distances will be 0. Okay, I don't get that, so let's read again. To measure the viewing distance from a given tree, look up, down, left and right from that tree. Stop if you reach an edge, okay, or at the first tree that is the same height or taller than the tree under consideration. Okay, if a tree is right on the edge, at least one of its viewing distances will be 0. Okay, if you are on the right edge, for example, looking to the right is 0. The elves don't care about distant trees taller than those found by the rules above. Don't care about distant trees taller than those found by the rules above. Okay. So you consider the middle of 5 in the second row. Looking up, its view is not blocked. It can see one tree. Looking left, its view is blocked immediately. Can only see one tree of height 5 right next to it. Yes. Looking right, its view is not blocked. It can see 2 trees. Looking down, its view is blocked. Eventually, it can see 2 trees. Yeah, because this is blocked here. Okay. A tree's scenic score is found by multiplying together its viewing distance in each of the 4 directions. By multiplying together its viewing distance in each of the 4 directions. For this tree, this is 4. Found by multiplying 1 plus 1 plus 1 times 2 times 2. Okay, well, however, you can do better. We consider the tree of height 5 in the middle of the 4th row. Looking up, its view is blocked at 2 trees by another tree with a height of 5. Looking down, its view is not blocked. It can see 2 trees. Looking, see 1 tree. Okay, the scenic score. What is the highest scenic score possible for any tree? Okay, so yeah, let's think about how we now compute this scenic score. So first, our trees have now this score, which is just an int, and it's 0 for the beginning. So what we can do, if we go through it, if we go to the left, then the question is, can we, if we go to the left, can we calculate the scenic score automatically? All right, so if we, for example, have a row of 0, if we are in the first row, we know that the scenic score to the top okay, maybe we do this differently. We calculate those in independent and then basically so we have multiple scores. Oh, these are not the scores, these are basically visible trees. Top, visible trees bottom, and then for left and right. Okay, so how can we efficiently do this? So the first easiest way would be just to do this brute force, right? So we go and we loop over these individual trees and then calculate this. Now let's do this. Maybe the okay. Yeah, I think this is not the nicest solution yet, but okay. Oh. So where we say this is y, and this is, no, this is y, and this is x. So, and then for now, for every tree, basically what we are doing, we are looping to the top for other y, which is y smaller until y greater equal 0. Minus y. So basically just implement this first for top, right? Where we try to figure out. And what the idea is, basically we go through all the individual trees that we have within our grid. And then from this tree we go to the top. So we go to the row before until we reach the end. And then we count basically how many trees we can see. So trees. So this means we check if g.fields oy from x dot height is larger or equal than the tree height, then okay, we probably need to fix something here. Minus, okay. So if the tree that we are looking at, and when we go to the top, is its height is greater equal the height of the tree that we are starting from, then it's basically break. So we say withable trees. Oh no, we say that our tree dot withable trees top is equal withable trees. So is this correct? So basically, given we start at the 0 row, then we initialize this with 0. We do this until -1, because we need to start one row above. So therefore we do this, we loop until we reach the top. And then basically we just else withable trees plus. So if we find a tree that is higher than the tree that we are currently looking at, then basically we just increase. Okay. So now let's do this in the same way for the other direction. So now it's basically going down. So where we say this is +1, and we do this until it's smaller than g.fields ln. Okay, and then we plus. Then we count the bottom. Okay, this should be it for the bottom. And now we do it for left and right. So first going to the left, x -1, x is greater equal 0. and OX is minus minus. Okay, we also need to make sure that we loop here over, change modify OY. Okay, and this is then OX and Y. And then basically we set withable trees left as withable trees. And now do the same thing when going to the right. So where we say we initialize this with x plus 1. We do this until OX, or as long as OX is smaller than len from G dot fields from Y, and we increase our X. Okay, so let's see. The tree scenic score is 8. This is the ideal spot for the tree house. Okay, let's see what we get here. We should also calculate this. Scenic score int, and this is then tree dot scenic score is equals tree dot visible trees left times tree dot visible trees right times tree dot visible trees bottom top times tree dot visible trees bottom. Okay. Okay. So now how do we print out what is the maximum? Let's do it that way, that we print scenic score. We would like to see basically the individual scenic scores of the individual trees. And this is something that we can calculate here in form of that we are basically let's see how those tree.scenic score, how we can reserve a number of digits, so how we can do the formatting of a number. This is something that I don't know yet, so let's take a look at Google. Golang format integer reading blanks. How to pad a number with zeros when printing. Okay, they are just printing pads. Oh, this looks quite nice. Just the number of that we want to have in between. Okay, this is good. So let's do this. Too easy, actually. Just say 3 should be enough. Okay, and then print scenic scores. Oh. Okay, maybe we should also use the test input first. Okay, this has a scenic score of 2, which isn't correct. So it should be 8, right? Ah, we didn't did we calculate the scenic score? Count visible trees. Yeah, maybe we split this up into 2 methods now. And we call this function grid calculate scenic score. And this is something that we also need to call here. Calculate scenic score. Doesn't look right, I would say. We have only one that has a scenic score of... Okay, maybe the counting is something wrong. Let's see. So basically, if we go to the next... Okay, visible trees is always 1, except if we are on the right side. Okay. We should count the tree that is high. We always, we additionally see the tree, basically, that leads us to stopping, looking further, right? But this is always a visible tree, so we should first count the tree and then break. Let's run. Okay, this looks way better. We have 8 and this is our ideal spot. I think this is somewhat right. Okay, run again. So now we have this here. Okay, and now let's run this basically on our input file. Okay. Okay, this is definitely some larger okay. Okay. We calculate now the scenic score, and we should also then basically, in the end, we are interested in the maximum, right? So we just return it. Max scenic score 0. If tree.scenic score greater than max scenic score, then we store it as a max scenic score equals tree.scenic score, and then we return max scenic score. Max scenic score is than max scenic score. Let's run. And our max scenic score is 250,000. Okay, this is quite large. Larger than I would have expected. But okay, let's see. What is the highest scenic score possible for any tree? Okay, correct. Good. So I think we are then done for today. Appreciate the time. So have fun and talk to you tomorrow. Bye.